Hi guys, welcome back. We are going to be taking notes, really short notes over free energy and equilibrium today, kind of tying up the first part of like Gibbs free energy and entropy, and then moving on today in our second video with electrochemistry. So let's go ahead and jump in. So guys, it's been a while since we've talked about equilibrium. So just a reminder that at equilibrium, there is no net change in the concentration of reactants or products. So what that means is reactants are still becoming products are still becoming reactants, but it's happening at the same rate. So our rate of our forward reaction is equal to the rate of our reverse reaction. So what does that mean for free energy? It's going to have this following relationship where delta G is going to be equal to negative RT times the natural log of K. All right, negative RT times the natural log of K. And R, if you guys remember, it's been a while since we talked about it, but R is our gas constant, and it is found on your periodic table under the gases, liquids, and solids section. And the R value we are going to use is 8.314 joules per mole Kelvin. And this is the one we're going to use because it's in joules and we're solving for free energy. So that's why we are going to use that one, where with our other gas values, we have like options that we can choose from. But we will use this R value. Okay, so quick review. When delta G is negative, that means that the reaction is thermodynamically favorable. But what does that mean, being thermodynamically favorable? It means that our reactants are going to turn into products. So it's thermodynamically favorable for the forward reaction. So for the reaction that takes our reactants and turns them into products. So that means that our K will be greater than 1 and our reaction will favor the product. So it's related. So if delta G is negative, K is going to be a big value, favor our products. Our reaction is going to go to completion essentially. Now, when delta G is positive, the reaction is not thermodynamically favorable. Again, that's for the forward reaction only. So that means our forward reaction isn't thermodynamically favorable, but our reverse reaction will be. So K will be less than 1, and our reaction will favor the reactants. When delta G is at 0, the reaction will be at equilibrium. Why? Because that should represent, when we're at equilibrium, it should represent the lowest value of free energy available to the reaction system. So the Gibbs of formation of our products minus the Gibbs of our reactants should be 0. And they should be, again, the free energy of the reactants and product should be equal when we're at 0. The other time that delta G is 0 is when we are doing a phase change as well. Okay, so we're going to take that equation we learned and the fact that at 0, it's 0 for equilibrium as well as phase changes. We're going to solve two problems together now. All right, so this first one says, given the reaction of when mercury goes from a liquid to a gas. So basically when mercury boils, that delta H is equal to 61.3 kilojoules per mole, and entropy is equal to 100 joules per mole Kelvin. Calculate the normal boiling point of mercury. Okay, so we just learned that during phase changes, delta G is equal to 0. So we can use that information and the fact that delta G is equal to 0 to be able to solve for what temperature would that happen at, and that would give us our boiling point. So we can use our equation. Delta G is equal to delta H minus temperature times our entropy. We can plug it in. So when it's 0, that'll be when we have this phase change going on. We have our delta H at 61.3 kilojoules per mole, minus, we don't know what our temperature is going to be. I'm just going to plug it in as a T, and times our delta S. Now remember, delta S is in joules here, but in order for this to work, we need it to be in kilojoules. So I'm going to divide by 1,000 to get it into kilojoules, and I get that my delta S would be 0.1 kilojoules per mole Kelvin. and then I just need to solve. So basically it would end up with 61.3 kilojoules per mole. Negative 61.3 kilojoules per mole is equal to negative T times 0.1. And so then solve for T. And I got that T would be 613 Kelvin, because we are in Kelvin there. But we don't want Kelvin, or it doesn't necessarily say, but if we wanted it in Celsius, we would just subtract 273. So 613 minus 273 gives us, gotta find it, 340 degrees Celsius. Boom. So, because we have that phase change, we can plug in our 0, and we're able to find our boiling point there, because it should be where delta G is equal to 0. All right? Okay, now for this problem, we're going to use our other equation, our other constant that we're looking at. We want to calculate the approximate standard free energy for the ionization of hydrofluoric acid, and we have our Ka value. All right, since we are given our Ka value, we are going to use that first equation that I talked about, that delta G is equal to negative RT times the natural log of K. All right, and this equation is also on your formula chart. There's several equations on here for delta G. I don't know if I'm showing correctly. There we go. There are, right here, are the different delta G equations. So it has the delta H is equal to minus T times delta S, negative RT ln K, and then another one that we're going to learn about in a little bit, in a few classes. All right, so this is on our formula chart. So delta G is equal to negative RT times the natural log of our K. So delta G is equal to, and remember our R value is a constant and it is found on your periodic table. Since we're looking for energy, we want to use the R value that does have joules in it. So we have 8.314. Again, that's just found in the gases, liquids, and solutions portion of the formula chart. And that is in joules over moles times Kelvin. And our temperature here would be 25 degrees Celsius. It used to be in Kelvin, so we add 273 to that, and we get that our temperature would be 298 Kelvin times the natural log of our K value, which our K is going to be 1.0 times 10 to the negative third. And so then you would just go ahead and plug that into your calculator to get our delta G. And I don't know why I keep forgetting to write G. All right, so plug it on in. And when you do, I got 1.7 times 10 to the 4th joules per mole. And again, it's joules because we're in joules up here, so it's going to be in joules. And then if you wanted to convert it to kilojoules, you would just multiply by 1,000, or sorry, divide by 1,000, and you would get 17 kilojoules per mole for your delta G value. All right. Okay, guys, the rest of this notes is a practice FRQ. I believe this is from the 2007 AP Chemistry exam. Pretty sure that's correct. So what I want you guys to do is this will connect basically what we talked about last class, the little bit that we covered up here, finished covering up here, and a little bit that we've covered in previous units as well. So I want you guys to set a timer for about 15 minutes. It's about how long you'll have on an FRQ of this variety. A little longer, but set it for about 15 minutes. See how far you get in the FRQ, and then check the answer key posted on Canvas to see how you did. I'll try to write out the pointing as well so you can point yourself and see how many points you would have gotten based on AP. All right, good luck, guys.